Let's go through lesson 5 of the second unit of the Advanced Functions course. This lesson is on families of polynomial functions. And in this section, we're going to determine the equation for a family of polynomial functions from its x-intercepts. Given additional information, specifically another point that lies on the graph of the function, we will be able to determine an equation for a particular member of the family of functions. Let's start by going through this investigation we have here. I have 2 sets of graphs. On each graph are 3 functions, so 6 functions in total. Each function is labeled with a number, so example, the red function is function 1, and its equation is written underneath here. We want to look at the graphs of the functions and the equations of the functions and see how, first of all, how are they related, and also what is similar between all of these graphs, and how could we figure out those similarities from the equations. So part A says, how are the graphs of the functions similar, and also how are they different? So what's the same between all of these 6 functions? Well, notice they all cross the x-axis at the same place. They all cross the x-axis at -2 and 1. So what's the same? They have the same x-intercepts. What's different between these functions, though, because they're clearly not all the same function. One difference we could talk about are the y-intercepts. Notice these 3 functions, they all cross the y-axis at different points. And same with these 3 functions here. So all 6 functions have different y-intercepts. So let's jot that down. So what's different? The y-intercepts. And also, it looks like the general shape of these functions have been stretched or compressed by some factor. So the general shape has changed too. So what's different? The shape of the function. Now let's look at the equations. Notice in the equations, they all have the exact same factors that include an x. They all have the factor of x minus 1. That's where the x-intercept of 1 comes from, because 1 is an x value that would make all 6 of these equations become 0. -2 is also an x value that would make all 6 of these equations become 0, because they all have a factor of x plus 2. Okay, well then why do they have different shapes and different y-intercepts? Well, that's because of the leading coefficients. Look, they all have different leading coefficients. We have a leading coefficient of 1, 2, a half, and -1, -2, a half. They all have different leading coefficients. That's what's changing its general shape based on the stretch or compression factor that's in front. And also notice the negative leading coefficients made the function open down. They're all going from Q3 to Q4. And the positive leading coefficients made them open up. They were going from 2 to 1. So describe the relationship between the graphs of functions of the form y equals k times x minus 1 times x plus 2, where k could be any real number. So it doesn't matter what we would plug in for k. All the functions that have these 2 factors would have the exact same x-intercepts. Part 2 of the investigation asks us to examine the following functions. This time it doesn't give us the graphs, it just gives us the 4 equations. It says how are they similar and how are they different? Well, notice all 4 of them have the factor of x minus 1, all 4 of them have a factor of x plus 3, and all 4 of them have a factor of x minus 2. So all 4 of them have the exact same 3 factors that involve an x. What does that tell us? It tells us they all have the exact same x-intercepts. They'll have x-intercepts of 1, -3, and 2. And it's important to note those x-intercepts are all order 1, meaning the exponents on them are all 1 as well. That's important. So what's the same? They have the same x-intercepts. But what will be different? Well, look at this constant factor that is in front of all 4 of them. This one has -2, this one has -1, this one has 1, and this one has 2. So they all have different stretch or compression factors out front of the factors of x. So what is that going to do? That's going to change the shape of the function by stretching or compressing it, and it may also change the direction, right? Because these are degree 3 functions. When the leading coefficient is positive, like in 3 or 4, the function would go from quadrant 3 to 1, but when the leading coefficient is negative, it's going to change the direction. So in these 2, it's going to go from quadrant 2 to 4. So what's going to be different? I'll say, but they will have different shapes and different directions. due to the value and the sign of that stretch or compression factor. And then if we were to look at the graph of all four of these functions, this is what they would look like. Notice they all have the x-intercepts at -3, 1, and 2, just like we said they would, but they all have different shapes based on the stretch or compression factor that we see in front of all four equations. So these four functions, we consider all four of these functions to be members of the same family because they all have the same x-intercepts with the same orders. So let's fill in the blanks here. A family of polynomial functions is a set of functions that have the same characteristics. Polynomial functions with the same zeros, so the same x values that make the equation be 0, are said to belong to the same family. The graphs of the polynomial functions that belong to that same family have the same x-intercepts, right? The zeros of the equation correspond to the x-intercepts of the graph. And I should point out the x-intercepts have to be of the same order. But these graphs of the functions that are part of the same family may have different y-intercepts because of the stretch or compression factor out front, this k value right there. So let's do a couple questions. Part 2 says represent a family of functions algebraically. Number 1, the zeros of a family, so the x-intercepts of the family of quadratic functions are 2 and -3. Determine an equation for this family of functions. So when we're writing the equation for the family, we know that the family of functions could have, so I'll call the function p at x for polynomial function, it could have any stretch or compression factor k as long as k is any real number. So we have to put a factor of k in front of the factors of x. And now I have to figure out what factors of x go here. I need a factor of x that when set to 0 and solved, I get 2. So that would be x minus 2. And I also need a factor of x that when I set it to 0 and solve, I would get -3. So that would be x plus 3. Do you see how the factor of x minus 2 creates an x-intercept of 2? Right, because if we plugged in 2, we'd get k times 0 times 5. That's 0. Now let's write the equations for two functions that belong to this family. So k could be any real number, so pick any real number you want. So the polynomial function could be 3 times x minus 2 times x plus 3, or let's pick another value for k that's any real number. How about 27 times x minus 2 times x plus 3. Both of those functions have the exact same x-intercepts with the exact same orders. They just have different stretch or compression factors out front. Part C says, determine an equation for the specific member of the family that passes through this point 1, 4. Let me show you in Desmos what I mean by this. Okay, so I have Desmos graphing the polynomial function right now that has a k value of 1. So I wrote the equation of the family, k times x minus 2 times x plus 3, and I let k equal 1. Notice it doesn't pass through the point we want, 1, 4. To get it to pass through that point we want, without changing those x-intercepts, right, because we need the function to have those x-intercepts, we just vary the value of k. So we need to figure out what value of k is going to make it go through that point 1, 4. I think it's going to have to be a negative value of k. Let's look. It's going to have to be, it looks like -1. How are we going to figure that out algebraically? What we're going to do is sub the point, xy, into our equation of the family for the functions and solve for what value of k satisfies that equation. So I will write 4 equals k times 1 minus 2 times 1 plus 3. I subbed 4 in for y and 1 in for x, and now I'm going to solve for what value of k satisfies this equation. So 4 equals k times -1 times 4. So that's 4 equals, well, -1 times 4 is -4. K times -4, I'll write that as -4k. Divide both sides by -4, and I get k equals -1. So the equation for the member of the family that passes through that point would have a stretch or compression factor of -1. So p at x would equal negative x minus 2 times x plus 3. That would be the equation for that member of the family. Let's try another one. 2. The zeros of the family of cubic functions are -2, 1, and 3. Determine an equation for the family. The equation of the family needs to have that k value out front as the stretch or compression factor that could be any real number. And then beside that k, I need the factors of x that create the zeros that it says in the question. So I need a factor that will create a 0 of -2. So that would be x plus 2. I need a factor that creates a 0 of 1. So that would be x minus 1. And a factor that creates a 0 of 3. That would be x minus 3. Part B says determine an equation for the member of the family whose graph has a y-intercept of -15. And remember, a y-intercept has an x value of 0, so this is really the point 0, -15. So once again, it gives us the xy value. Let's have a look in Desmos again, just to see what we're going to want to get for our answer, and then we'll figure out how to get that algebraically. All right, I've written the equation of the family. I've put that k parameter out front, and let k be 1 for now. And notice that k value of 1 is not letting the function go through that y-intercept we want. It's got the correct x-intercepts, but it's not going through the correct y-intercept. So we have to figure out what value of k will stretch or compress this function so that it goes through that y-intercept. And notice no matter what the value of k is, it's not changing the x-intercepts. And it looks like a k value of around -2.5 is going to get me through that y-intercept and keep the x-intercepts the same. So let's solve for that algebraically. So I'll need to plug in the y value of -15 and the x value of 0 into my equation for the family of functions and solve for k. And when I do this, I would have k times 2 times -1 times -3. So I have -15 equals 2 times -1 times -3. Well, that's 6, so I have -15 equals 6k. Divide both sides by 6, and I have -15 over 6 equals k. 3 goes into the numerator and denominator. It goes into the numerator 5 times, so -5 over, and 3 goes into 6 twice, so -5 over 2. So my k value is -5 over 2, or as a decimal, that's -2.5, whatever you would rather. So my final equation for the member of the family that passes through that y-intercept is p at x equals -5 over 2 times x plus 2 times x minus 1 times x minus 3. There's my final answer. Part D says, sketch the graph of the function. Now I've already showed you the graph in Desmos. Here it is, but how are we going to generate that? Well, we know what the x-intercepts are. It told us them in the question, and we can also see them from the equation here. We have the x-intercepts of -2, 1, and 3, so we can plot those, -2, 1, and 3. I know each of the x-intercepts is order 1 because of the exponents on the factors of x, so I know it's going to go straight through each of those x-intercepts. All I need to know is the end behavior. Well, it's a degree 3 function. If I add the exponents on the factor of x, I can see that. So this is a degree 3 function, so it's odd degree. And the leading coefficient would be -2.5 times 1 times 1 times 1, so -2.5. So the leading coefficient is negative, so I'll write negative leading coefficient. That tells me that the end behavior for odd degree with negative leading coefficient is from 2 to 4. So I have to start up here in quadrant 2 and finish down here in quadrant 4. I need to pass straight through each of those x-intercepts. So the graph would look... Oh, and don't forget we also know the y-intercept is -15. So the graph would look something like this. And let's compare that to our graph in Desmos. And notice it's very similar. Turning points are in the exact right spot, but correct end behavior, correct x-intercepts. Number 3 is probably the most difficult question in this lesson, so let's take our time going through this one. It says determine an equation for the family of cubic functions with zeros at 3 plus or minus root 5 and -0.5. So this is the first time we've had an irrational 0. Let's see how we do this. So I'm going to first figure out what are the factors that would create these zeros. And remember, there are 3 zeros here. 3 plus root 5, 3 minus root 5, and -0.5. So let's figure out the factors first. And this is the first time we've really had to show work for figuring these out. I need to figure out, let's start with the -0.5 zero. There is some factor that when I set it to 0 and solved, I got -1 over 2. What was that factor that had this solution? So I need to reset this back to 0. So let me multiply the 2 to the other side. and then add the 1 over. So I get 2x plus 1 is the factor that when set to 0 and solved, right now envision going the other way, if I set this factor to 0 and solved it, I would get negative a half. So 2x plus 1 is a factor. So 2x plus 1 is the factor that creates the x-intercept of negative a half. What factor would create those two irrational zeros? Well, let's do the same process. Let's say x equals 3 plus or minus root 5. I know this is what I get after the factor has been set to 0 and solved. Now I just have to work backwards. Where did it come from? Let's reset it back to 0. So let's subtract the 3 over. So I have x minus 3 equals plus or minus root 5. Now I need to move the square root over. And what's the inverse of square rooting? Squaring. So we'd square both sides, and what we'd have is x minus 3 squared equals 5. And now we actually have to expand this x minus 3 squared. And remember, x minus 3 squared means x minus 3 times x minus 3. Now you don't actually have to show that line, but I just want to remind you of that. Don't just try and put the squared on the x and the 3. That's not how it works. You actually have to FOIL this out. X times x is x squared. X times negative 3 is negative 3x. And then this negative 3 times x, we get another negative 3x. And this negative 3 times negative 3, we get positive 9. So I have x squared minus 6x plus 9. And then I'm going to bring this 5 over, so it's plus 9 minus 5. And collect those constants together. I get plus 4. So this right here is the factor that if we were to set it to 0 and solve, we would get the zeros of 3 plus or minus root 5. And if you don't believe me, try quadratic formula to solve this. You will get 3 plus or minus root 5. So x squared minus 6x plus 4 is the second factor. So the equation for the family would be p at x equals k times 2x plus 1 times x squared minus 6x plus 4. That's the equation for the family that has x-intercepts at negative a half coming from that factor and 3 plus or minus root 5 coming from that factor. And of course this factor doesn't simplify, right? Nothing multiplies to 4 and adds to negative 6 because we know it has irrational zeros, so it's not factorable. Last part, part 3, determine an equation for a function from a graph. So in the previous parts, I just told you about it in words. Now we'll look at the graph. This one has x-intercepts at negative 3, negative a half, 1, and 2. Determine an equation for the chordic function represented by this graph. So I could write the equation for the family of functions that has those x-intercepts. So it would be p at x equals k times x plus 3. That's the factor that would give me the x-intercept of negative 3. Which factor would give me an x-intercept of negative a half? It's actually 2x plus 1. And we talked about that right up here, right? We explained that in the previous question. And then we have a factor of x minus 1 and x minus 2. Those would create those two x-intercepts. Now, a lot of people will say for instead of 2x plus 1, why not do the factor of x plus 0.5? That has the same 0, right? Negative a half makes this factor and this factor both be 0. So they create the same x-intercepts, I agree. And you could do x plus a half. It's going to get you a different k value, but as long as you calculate properly, your final answer will end up resulting in the same graph. And I'll explain that more as we go. For now, let's just work with what I have in red. Now I need to find the member of this family that passes through, I need another point on this function. I can't use one of the x-intercepts, I need another point, and it looks like this one's labeled for us right here. This is the point negative 1, negative 6. So I'll plug in negative 1 for x, negative 6 for y, and solve for k. So I have negative 6 equals k times 2 times negative 2 plus 1 is negative 1 times negative 2 times negative 3. Let me simplify all those factors on the right. 2 times negative 1 is negative 2, times negative 2 is 4, times negative 3 is negative 12. So I've got negative 12k on the right, divide both sides by negative 12, and I get k equals a half, or 0.5, however you want to write it. So my final answer for the member of this family, p at x, would be equal to a half times the 4 factors of x plus 3, 2x plus 1, x minus 1, and x minus 2. Now let me backtrack to what I told you about this factor of 2x plus 1. If, while you were doing this question, you decided to, instead of doing 2x plus 1, you decided to use x plus a half, let me just write that out, you're going to get a different k value. And in fact, the k value you get is going to be twice as big. Let me explain to you why. Well, look over at this red equation here. If from that factor I common factored out a 2, it would make it look like that factor. Let me show you. So a half times x plus 3, and let me common factor a 2 out from that factor. So 2, and then divide both of the terms in there by 2, and that will give me x plus a half. And then I still have the x minus 1 and the x minus 2. So I have a factor of 2 times a factor of a half. That's 1. So it would be 1 times x plus 3 times x plus 0.5 times x minus 1 times x minus 2. So if we had a factor of a half, if I went ahead and solved this, and let me just do it quickly by plugging in the y value and the x value, we'd get a k value of 1, which is what we see as the structure compression factor there when we have the factor of x plus a half. Now, I don't want you to use the factor of x plus a half. I'd rather you use 2x plus 1. But I'm just showing you that you could get an equivalent answer. And in fact, let me prove to you in Desmos that they are equivalent. Okay, there's the equation of the way I want you to solve it. And now, if you had have done the factor of x plus 0.5 instead, notice the k value of half is not going to give you the correct graph. A k value twice as big because we would have common factored out a 2, so instead of a half, make it 1. Notice, hey, that's the same function. In a question like this, I would take that answer or that answer, but I want the first one. I would rather this one. So for this question that we wrote out together here, you can stop what you copied down right after the circled part. This blue stuff and below here that I just scratched off was just to show you what would happen if you had have chosen a different factor. Okay, that's it for this lesson. Make sure you try out the practice questions.